So, hello students, my name is I am starting new topic today. So, my new subject I am starting computational fluid dynamics. First, step by step, we will understand what is the outline course of this CFD. So, first we will learn about what is CFD, where we use CFD, what are the basic application area of CFD, and then how CFD code work, and then how that particular physics will work over there, and then some basic outline about the CFD code generation. Okay, so this is very introductory and very in easy language. This I have designed this complete syllabus, so you can easily understand the complete subject computational fluid dynamics. Although students, you have studied fluid dynamics and heat transfer subject in your basic engineering, but here this is some more advancement in fluid dynamics and heat transfer area. So first, what is CFD? First, what is CFD, students? So computer simulation for prediction of fluid flow phenomena. So in earlier days, when this complete physics design for particular fluid flow phenomenon or particular heat transfer phenomenon or chemical reaction, in those days it was very difficult to manipulate the results for intermediate points. Generally we focus towards initial points and final points, but if you have to see the complete picture of the fluid flow, then it becomes very difficult for us, because during those time our mathematical computation, it is very limited. But due to the advanced computer, we have now the computational power. So through that computational simulation for prediction of fluid flow, it becomes very easy. So fluid flow, it is model for partial differential equation. As we have studied about governing differential equation of fluid flow, in your governing differential equation of fluid flow, you have studied some partial differential equation in the form of your conservation of mass, conservation of momentum, and conservation of energy. So what we do in computational fluid dynamics, fluid flow is model for partial differential equation and describing the conservation of mass, momentum, and energy. All your computational fluid dynamics is to learn about how to develop code for conservation of mass, conservation of momentum, and conservation of energy with conservation of chemical species also. But here, because in our mechanical engineering we strict mainly in your conservation of mass, conservation of momentum, conservation of energy, so that's why I focus on conservation of mass, momentum, and energy only. So the objective of CFD is what? The objective of CFD is to model the continuous fluid with partial differential equation and discretize partial differential equation into algebraic problem. How to discretize this partial differential equation into algebraic problem? Using Taylor series expansion. So the Taylor series expansion, I think you have studied in your lower classes in your mathematics. So that f of x plus delta h, and then the proceed. Here we solve this partial differential equation and convert this into algebraic equation, and after converting this into algebraic equation, what we do? Solve it and validate it. It is very important. After solving, we have to validate. It is very important part in computational fluid dynamics, and achieve simulation based design, and finally we achieve simulation based design. This is the what basic of your computational fluid dynamics. Now what is your continuous fluid? It is very important. So we have studied that continuum concept. What is continuum concept? In continuum concept, we assume that our mean free path, it is tends to mean free path, it is tends to 0. What it means, mean free path? Mean free path means a hypothetical sphere and the two fluid molecule will interact with each other in that hypothetical sphere, and the distance covered after colliding with each other, so that complete radius, this is called your mean free path. And then the ratio of mean free path upon characteristic length. Characteristic length means what? the distance, statistical distance between the two molecules. This ratio, what is mean free path upon characteristic length, it is Nugget number, and if Nugget number is in order of 0.01, then we say our fluid flow it is in continuum. Okay, so what is the simple meaning of continuum? We can discretize our continuous function, in with respect to space and time. Okay, that is nothing but continuum. Very easy. We can discretize our fluid flow property with respect to space and time. Okay, this is basic regarding your continuous fluid. Okay, about why we use CFD. Although we have various types of experimental setup, various types of our scientific algorithms and all this is we have, but why we use computational fluid dynamics? For analysis and design purpose. This is the first important basic headline we can say, analysis and design purpose. So simulation based design instead of build and test. So earlier what we do, whenever we have to design any particular system, we have to build some model then analyze. But during this build and test, this required too much cost and at the same time too much time also. In place of this, using your computational fluid dynamics, we can simulate based on design instead of build and test. So more cost effective, that's why it is more cost effective and more rapid than your experiments. Rapidly you can give your results. Okay. Then CFD solution provides high fidelity database for your interrogation of fluid flow. Okay. So what it indicates, CFD solution provides high fidelity database means earlier when you do any test, so during that test you have to focus on initial and final state only or intermediate some specific states. But in computational fluid dynamics you can see the complete picture. So you have a very wide database through which you can design any particular space or any particular design part. Okay, so that is the advantage of CFD. Simulation of physical fluid phenomena that are difficult to measure by experiments. So there are some experiments which is very difficult, very hazardous, very cumbersome in mathematical exercises. In that case also you can use CFD. So commercial package CFD, there you don't have to do any mathematical manipulation. You can easily provide your boundary condition and you can see the results also. So scale simulation, full scale ships, airplane. So it is very difficult to see the model, just like your wind tunnel test. This is very exhaustive simulation. Okay. Simple hazardous, explosives and radiation and pollution. In that case also you can do CFD simulation. So it is very advantageous. Second, physics. So about physics, weather prediction, it is now becomes very important tool. CFD becomes very important tool to simulate your weather prediction results. And we know that nowadays it is very challenging also. Okay, so planetary boundary layer, stellar evolution, this is other examples of CFD where we can do this CFD simulation. So knowledge and exploration of flow physics. There are certain scientific assumptions also, so particle track, and then we have to analyze particular particle track. So this is all about knowledge and exploration of flow physics. In your biomedical fields also you can use CFD. So in next slide we will see where and how we can use this CFD in various types of application also. Next important, where CFD used. So there are various wherever fluid flow is there you can simulate, and there you can see the results, and there you can design, and there you can explore your CFD. So some important application area, it is aerospace. First important application area, turbomachinery, aerospace. This is very widely used tool. Okay, appliances, aerospace appliances, at the same time automotive, biomedical field, then chemical field, chemical processing fields, then HVAC, that is heating, ventilation, air conditioning system design, and then hydraulics, and then marine engineering, oil and gas engineering, power generation, sport. So some pictures are there, you can easily understand through the pictures. So you can see here that how we can see the result flow over the aeroplane. So you can see easily, so where the pressure drag will be there, where the high thermal stresses will generate it, where in how in which velocity there will be a continuous fluctuation, air drag and lift and drag, all that type of smallest and tiny results you can see with the help of computational fluid dynamics. Second, automotive engineering for fast track vehicles. There also you can easily understand how CFD can give you a better and very precise results. At the same time, bioengineering, nowadays coronavirus, this is very hazardous. Experimental analysis are there which is very hazardous for human health. If they do their simulation, then it becomes very easy and non-hazardous also. So there we can use your CFD simulation. Okay, so how much amount of particle will flow, and what will be the porous media of your mask, and how you can defeat all this type of viruses. Through this you can easily understand that with the help of CFD you can analyze your fluid flow in your biomedical field. Okay, similarly for HVAC system in building design also, in interior building design, outer building design, there also you can use CFD. At the same time, flue gas path, if there will be any if there will be a fire in particular building, so how smoke will travel through that building, if that building will be very large, 50-story building or 70-story building. In that case also you can use computational fluid dynamics. At the same time, sport, the spinning of your ball, at the same time football, and same time various type of tennis, cricket, everywhere you can use, wherever fluid flow will be there, you can simulate that result and you can see how your result will be. Okay, at the same time, turbo machinery application. Okay, your different type of turbine, compressor, and then different type of turbo machinery application. There also you can see the different type of fluid flow results, through which your simulation become very easy. Now physics. So very important part, how your CFD will work, that is very important. So CFD codes typically designed for representation of specific flow phenomena. Okay, so we can restrict our CFD simulation also. How? So we can use incompressible flow, but some of the application where we cannot use incompressible flow, so compressible flow also we can use. Okay, similarly viscous flow design, where viscosity will be dominant over inertia and other part, there also you can simulate. Okay, similarly in viscous type of flow, okay, non-viscous type of flow, there also this will limit your results. If you don't want to do compulsive mathematical exercise, in that case you can use your approximation. So for that approximation, inviscid flow or your laminar flow, these are some approximation, but generally we know that our fluid flow, it is turbulent in nature generally, because laminar flow, it is orderly and very slow flow path velocity. So that's why your majorly your fluid flow applications are turbulent in nature. So turbulent flow you have to study. So in that case it is very cumbersome mathematical exercise. So but if it is required, then you have to do. So turbulent flow, laminar flow. Okay, so this in bracket you can see how you can check this. So Reynolds number will give you the turbulent or laminar type of flow. Incompressible and compressible flow you can see from Mach number. Similarly single and multi-pass flow, or your one phase flow, two phase flow, multi-phase flow. So in this way you can see and explore various types of fluid flow application. Thermal density effect and energy equation, Prandtl number, Grashof number, all these type of numbers are there through which you can see thermal diffusivity is larger or momentum diffusivity will be larger or other types of application. Wherever it is according to your requirement which you want. Then free surface flow and surface tension, Froude number, Weber number. Okay, then chemical reaction, mass transfer, all this is all are about specific flow phenomenon where you can design your CFD code. Next important, physics. So we know that if we discretize fluid mechanics, so it will be your incompressible and it will be your viscous and non-viscous. It is compressible and incompressible also. It is on the basis of viscosity. So it is inviscous or viscous. Inviscous means non-viscous. Okay. So in viscous flow, compressible, incompressible. Then about it, internal type of flow, external type of flow. Internal type of flow, example, it is pipe flow. External type of flow, it is fluid flow over the flat plate. It is one of the example of external flow. Fluid flow over aerofoil, fluid flow over the ship. Fluid flow passes through your building passages. This is all about external flow. Viscous flow, it may be laminar or it may be turbulent. This is all physics behind your fluid mechanics. Now about how CFD code works. Okay, so about how CFD code works, if you have to understand, so there are three main steps for CFD code generation. It is pre-processing, solver and post-processing. So what is pre-processing? In pre-processing part, first we have to make one computational domain. Okay, so after making your computation, why we use this computational domain? Where we do our experimentation. That is very important. Na? So that's why first we will make our computational domain. So in that particular computational domain, we have to define that particular computational domain and then grade generation, that is mesh. Okay, we have to discretize this computational domain is small elements or nodes. So it will be based on your solver. It may be FDM, FEM or FVM. So accordingly you will give the name, but grid generation it is important part. Then definition of fluid property you have to define. This is primary pre-processing. Then specification, appropriate boundary condition. You have to apply the boundary condition. This is all about your pre-processing. You can see picture where we can see that one helical coil is there. We have mesh it. Okay, that is discretize this computational domain. Let us assume fluid flowing through helical coil. So for that purpose we have to discretize this helical coil. So in small elements. So it may be 1D, 2D or 3D. So in all the three dimension we can discretize. Second, solver. So mainly solver it may be FDM, FEM and FVM. So we will later on understand this, what is FDM, finite difference method, FEM, finite element method and FVM, finite volume method, and which is very generous nowadays for our computational fluid dynamics code generation. Okay, so approximation of unknown flow variable by means of simple function. We have to define the function. It is very important. To solve any particular discretized equation, you have to form one function, and discretization by substitution of the approximation in the governing flow equation. So first we have to assume some approximation. So we can see this first level, what is first level, second level approximation, why we do approximation for fluid flow simulation. Okay, so we will see later on. Okay, next it is solution of the algebraic equation. And then post-processing results. So post-processing result will be 2D, 3D surface plots, and then your view manipulation, then contour plots, then your vector plots, then your particle tracking. All these you can see easily with the help of post-processing results. Okay, for today it is sufficient. In next lecture we will understand about your governing equations. Okay, thank you very much.